It's a pleasure to be here. Maybe I'll just move that back a little bit and talk to you today about work that Alexa Alexander and I have been doing on water quality in tributaries to the Athabasca River in relation to oil sands activity. So let me just start and perhaps remind many of you about the reports that have come out over the last few years that have identified the need to establish baseline conditions for water quality as well as ecosystem health in order that we can use those baseline conditions to assess future changes. Those reports really led to the establishment of the Alberta-Canada Joint Oil Sands Monitoring Plan, which posed specific questions for water. And those specific questions are shown here. Ones that focus on the current state of the water, how has it changed, what contaminants are entering, and cumulative effects. What I'd like to do in the course of the talk today is really focus on the last two questions that were posed, the long-term trends in water quality in tributaries of the Athabasca River, and then also the aspect related to the cumulative effects of man-made discharges. And I'm going to do this looking at it using a historic data set, and specifically, what I'd like to attempt to do then is to look at how water quality or water chemistry specifically has changed in relationship to the types of oil sand development, and I'm going to bring in the open pit operations as well as the steam-assisted gravity drainage, SAGD. I'm usually thinking of it in the acronym. So look at the effects of the different types of mine operations as well as looking at the stages of mine operations. So moving from pre-development when there is no mining to the early stages of operation, which are largely ones related to land clearing, to expanded or subsequent development. I'm going to make use of the extensive historic water quality data that has been captured over, about 40 years now. Not to say that we don't have a lot of data coming in the last 3 years, but I'm going to touch upon that more at the end of this presentation and tell you where those data stand. But essentially a bit of a recap to say that monitoring has been going on in the tributaries of the lower Athabasca River since about the late 1960s. I think Alberta Environment started monitoring in the early 1970s, and then its monitoring was sort of encapsulated and became foremost as part of the Regional Aquatic Monitoring Program that was established in 1997. We used the data from Alberta Environment and the RAMP program to establish a data set to indeed ask the questions about changes in water chemistry over time. So we took those two large data sets and then we sort of pared them down using the schema that I'm showing on the slides. Essentially, we excluded the very small rivers, those ephemeral rivers, but we also excluded the larger rivers from the data set. We excluded the winter time period because there were rarely many samples captured during the winter period. And we also excluded extreme outliers in the data set unless they were specifically addressed with field notes that may have explained why these unusual numbers were seen. We also excluded sites that were very infrequently sampled, in other words, less than 3 times. So this brought our data set down to still 96 sites and over 3,500 samples and 417 parameters. We then went through a parameter selection exercise. As I said, the number of parameters in the data set started at 417. We then went through and excluded parameters if the analytical methods, particularly detection limits, differed between agencies. We excluded if many of the many of the water samples weren't measured for a particular parameter. We also excluded if many of the samples exceeded the detection limits. Were below the detection limits. And finally, when we got down to this number of 36 parameters, we did a canonical analysis to see which of those 36 parameters showed any relationship to the geological formations, to the position, be it upstream versus downstream of the McMurray Formation, or to the development going on in the region. So this then pared our data set down from the original 417 parameters and funneled it down to now 14 parameters. And I've listed those 14 parameters on the bottom side of the blue box on the left. You can see them there. But for the purposes of this talk today, What I'd really like to do is focus on 6 of those parameters, the ones that are shown in a highlight. So dissolved selenium, total and dissolved arsenic, dissolved boron, total uranium, and total vanadium. And the reason I'm going to focus on those 6 is because they're ones that have been identified as being indicators of oil sands activity, oil sands development. And in fact, we heard from just a moment ago from Colin about the role of, or the indicator value of total vanadium. So I'm going to look at those 6 parameters then in this talk, but in fact our work which is being written up includes the other 14 parameters that I've mentioned, as well as dealing with the 36 that came out of the parameter selection exercise. Oops, let me go back again. For each of the sites, and as I mentioned, we pared down, we had 51 aggregate sites. For each of these sites, we went through a site delineation exercise, and we identified for each site the geological formation on which it was situated, the mining activity that was present upstream of the site, be it open pit, SAGD, or multiple mining activities. And we also, from various reports and agencies, determined the stage of mine development throughout the years that site was operational. For each site, we estimated discharge, and then discharge was used to normalize the concentration data to give us information on instantaneous daily loads. So just to give you an overview of what our final data sets look like, it's shown here in a summary version in this slide. And you can see then that we have data from 7 rivers, and I've grouped it for the period, I've grouped it by upstream versus downstream. Now clearly upstream is upstream of development, so there was no development occurring during the data, in these rivers in the upstream portion. But I've further divided the downstream portion of the river into 3 time periods. Pre-development, that deals with the period before any development occurred in the downstream portion of the watershed. And then there's also early development, which is the period when it's largely land clearing, but also road, pipeline, and infrastructure construction. As well as in the case of open pit development, it was excavation of the pit and dewatering. And then there's another time period, which I'm referring to as subsequent expansion, which really refers to when the mine was operational, but there is also something else occurring. It could have been further land clearing, added infrastructure, or increased production. So you'll see me come back and talk again about these upstream versus downstream, and then within the downstream, the pre, early, and subsequent development. Well, using this data set then, we were able to ask, or at least pose several questions. And I'd like to walk through each one of these questions in turn and then give you the answers to the questions. The first question we asked, was can we pool the upstream and the downstream pre-development data to establish reference condition? Well, it seems somewhat obvious to think about. The upstream, there is no activity. The downstream, prior to development, there is no activity either. But really, it's a little bit more challenging than this, as shown in this slide here. And I realized after I drew it, I felt like I was doing semaphore and trying to give a code in semaphore. But I'm trying to get across the geological formations that are occurring upstream of each of these sites. And simply to point out what we really needed to ask then, was there any differences in chemistry from upstream versus downstream relative to the McMurray Formation? So our sites grouped into ones that were upstream of the McMurray Formation, and those are the red box showing upstream. And then we had downstream sites, the downstream pre, that were either within or downstream of the McMurray Formation. So we were able to ask, does position relative to the McMurray Formation affect the concentrations of our parameters? Moving on then, we posed a second question. Assuming that we could indeed pool the upstream and the pre-development to establish reference, we could ask then, do reference samples differ from samples collected during early development versus subsequent development? So you can see then we ask reference, does it differ from early? Does it differ from subsequent? And then moving on even to a bit more finer resolution, we posed a third question. And this question was, well, does reference differ from open pit operations, which is the beaver, the muskeg, and the steep bank? Does reference differ from SAG-D operations, and that's the sort of pinky colored periods for the L's and the Firebag River? Or does reference differ from multiple mining activities, which is the greeny boxes shown for the Christina, which has multiple SAG-Ds, or the Mackay that had open pit and SAG-D operations? So those are the three questions that we were to ask with this data set. Well, then let's answer each one of those in turn. And what you're going to see is a series of slides, and they show the 6 parameters of interest, and you can see them labeled: total arsenic, dissolved selenium, dissolved boron, total uranium, total vanadium. So there's 6 panels. And then along the y-axis, there's either concentration or, in this case, instantaneous load. And here we're asking the question, what is the influence of the McMurray Formation? And the slide shows the open bars, which are the samples from upstream of the McMurray Formation, and the yellow bars, which are the samples from the downstream of the McMurray Formation. And I think you can see that what we saw was there was no significant difference when we looked at instantaneous daily load, or if we looked at concentration corrected for distance in these parameters. So in other words, concentration normalized for either discharge or concentration normalized for distance didn't differ between samples collected upstream or downstream of the McMurray Formation. Now let me point out that's just for these 6 parameters. I don't want anyone to go home and think that applies to every parameter that could be sampled in these rivers. So knowing this then, we could indeed pool our upstream data and our downstream pre-development and establish a reference condition. And that's what's shown here in the open bars on the left side of each one of these 6 panels, is the reference condition, the instantaneous daily load expressed as a reference condition. And I'm comparing it to the early stage of development, which is shown with the E under it. I'd point, but I don't think I can get it to all the slides here. Or the subsequent stage of development, which is shown with the S at the bottom of the panel. What you can see then, if we compare the early stage of development, all early periods differ from the reference concentration. The only period that differs from reference when we look at the subsequent is the dissolved boron, which is shown here in yellow. So the yellow bars then for earlier subsequent are the ones that differ from reference. So all early stages then differ from reference, whereas only dissolved boron in a subsequent stage differs from reference. And then moving on, and getting even, I'm afraid, a little bit more complicated, is addressing the question is whether reference samples differ from samples collected from open pit, downstream of SAG-D, or downstream of multiple operations. And I'll try and walk through this a little bit in more detail and highlight, to begin with, the data from where there's differences downstream of the open pit operations. The yellow bars are indicative of concentrations that are significantly different from reference. And you can see in the case of the open pit operations then that there's significant difference in dissolved boron in the early stages of operation, and dissolved selenium and total uranium in subsequent operations. Moving along then, and now looking at the SAG-D situation, there's 2 parameters that show a change compared to reference, and you can see that's for total uranium and total vanadium. And then finally, looking at the multiple operations, the rivers with multiple operations, there's also 2 parameters that differ from reference, the dissolved selenium and also the total uranium. The other aspect we tried to do as part of this work was compare the downstream concentrations in our 7 study rivers to guidelines. And we wanted initially to make the comparison to the Canadian Council of Ministry of the Environment guidelines. However, they exist for only 2 of these parameters, that being total uranium and total arsenic. So what we've done here is made comparison to the downstream concentrations to the reference concentrations plus 2 standard deviations, which is a method that's sometimes used in the absence of guidelines. And you can see then, if you look at data for all the parameters from the pre-situation, there's several several that exceed the reference concentration. The percentage that exceeds ranges anywhere from 0 to 8%. And then when you look at post-development, you'll also see a few exceedances. In the case of total arsenic, dissolved boron, the percentages have gone down, the number of exceedances have decreased, whereas for 2 parameters, total uranium and dissolved selenium, the percentages that exceed have increased. And when you break that down and look at it by mining type, and you can see that there's been a few increases associated with each type of mining. So there's been an increase in frequencies of exceedances for 3 parameters in open pit mining, that's the red arrows going up, for 2 parameters in the case of SAGD operations, and for 4 parameters in the case of watersheds with multiple mining operations. Well, let me try and summarize and bring this all back together again then. And say our first question, the answer to that, was that the differences in the 6 parameters that we examined can't be attributed to their position relative to the McMurray Formation. In other words, any increase in downstream loadings following mine development is unlikely to be natural in origin. Our second question showed that increases in our loads tended to be most associated with the early development period, so the early land clearing stage of operations. And our third question looked at the effects of the different types of mine operations and the water and the exceedance of reference conditions, and we tended to find fewer instances of elevated concentrations with the SAGD operations compared to the open pit operations, particularly when you look at the larger 14-parameter data set rather than just the 6-parameter data set when I presented here. Well, as I mentioned, I was going to allude to the water chemistry data that's coming in under JOSM, and we've had a very intensive 3 field years sampling over from spring of 2012 until, well, we're ending just about now, and we've sampled very intensively during snowmelt on a daily basis, and then gradually backed off as the hydrograph retreated. And we now have these very intensive, very consistent data collections that we're working on analyzing to be able to answer the questions, the specific questions that were posed under JOSM, looking at trends over time, validating reference conditions, and recommending sample frequency. Well, I think I'll stop there, and I'd like to thank a number of folks who've been involved in the work, but particularly Alexa Alexander, who's not here, who undertook a lot of the analysis that formed the basis of this presentation and our paper that will be hopefully coming out shortly. Thank you.